Today we're going to be talking about electron configuration. I know that a lot of you guys took that quiz, and I saw a lot of confusion going on, right? As well as I just wanted to give you some context for this and kind of some shortcuts and a little bit of easier ways to deal with electron configuration, because there are shortcuts, right? And it's important to understand the background, but it's also important to know the shortcuts, at least I think. So we are going to look at this PowerPoint here, and our objectives today are going to be identify how electrons behave in their energy shells, write electron configurations for some elements, learn the shortcuts, and we're going to draw the relationship between the valence electrons and the Lewis structure. So you are going to want to have a periodic table handy. I personally would recommend that you print out a blank periodic table, or you have one saved on your bookmarks, right, that you could draw on or color or circle, because that's going to help you tremendously with the shortcuts. So our warm-up question is taking a quote from the Canvas lesson here. All systems in nature tend to take a position or arrangement that has the least possible potential energy. I want you guys to take a second to read that again if you need to, and think about what that means, and suggest in the chat what that means in your own words. Could be an example, could be just rephrasing it in your own words, but really think about what that means. I'm relocating so I can be next to the periodic table. So what do we think? What does this mean? I'm going to offer a possibility here, and you guys tell me if you agree or disagree. Do you think that that could be an interpretation of this? The universe is lazy. All right, so we got a lot of silence. Hopefully at least got you thinking, right? I think this is a viable way to interpret this. The universe is lazy, right? Everything is going to sort of take the easiest way without getting too much potential energy, right? And in this case, the best way that I could describe this, and that we will really specifically reference here for electrons, is think about when you're getting on a bus, right? Let's say you're getting on a bus, and there's 3 people seated on the bus, right? And there's a bunch of empty seats. Are you most likely to, A, go sit by a random person on the bus, or B, take an empty row to yourself? Let me know in the chat. A, you're going to go sit by a stranger. B, you're going to take an empty row. Yeah, B, or take the empty row, of course, right? You're only going to sit by that stranger if you have to, right? If the bus is packed and there's one open seat, all right, you're taking it, right? But if there's a bunch of empty space, why would you sit next to the stranger, right? If it's your friend, sure, then you're going to want to sit next to them. That's a different situation, right? Electrons don't have friends, so they don't have that issue. But the concept here is you're going to choose to be by yourself, right? Not interacting with anyone else unless you have to interact. And that's kind of how the electron feels, right? Except that's how they feel all the time. And yes, they don't really have feelings, but we're going to make them personified today to be like a person. So, that's my quote that I wrote. I was trying to erase it. It doesn't work that way. So what do electrons want and what do they do, right? Clearly, I am personifying them because electrons are not people. But they want the lowest energy level possible, putting them as close to the nucleus as possible, right? We know they're floating around in this cloud outside of the nucleus, but yet they want to be as close to the nucleus as possible. Why do you think they would want to be so close to that nucleus? What's going on in the nucleus that electrons would be interested in? High energy. That's a good guess. There is a ton of energy in the nucleus, right? You know what else there is? Positive charges. There's a bunch of positive charges. And what do electrons like? Positive charges, right? They're attracted to positive charges. So of course they want to be close to those positive charges, but at the same time, they don't want to be next to each other, right? They want to be as close to the positive charge as possible with no other electrons around, which is impossible, right? Because especially if you're an atom that has 50, 60, 70 electrons, they cannot all be next to the nucleus, or they're going to have to be next to each other, right? So electrons will fill these energy shells in order to keep their space, right, but still maintain that proximity to the nucleus as much as they can. And the arrangement of these electrons, right, the way that they end up positioning themselves actually helps determine properties and actions of elements, right? That's why some elements have certain properties, right? Maybe they're super reactive. They explode when they come into contact with things. Perhaps they don't react at all, right? Maybe they're really commonly formed into salts, right? All these different properties, including melting point, boiling point, right? All these ability to dissolve in water, et cetera, are all going to be determined by these electrons, which is why we actually care about studying them. And this is hard to do, right? In fact, a lot of this electron science is from it within the last 50 years, because you guys read about the model of the atom and kind of how it developed, right? It took a while to figure out that the electrons were on the outside. And then it kind of took a while to find out what they're doing because they're moving at all times, right? Never are they still. Meanwhile, the nucleus isn't really moving. So we could easily look at that and say, oh, okay, there's protons and neutrons. They're just there. They're chilling in the nucleus. Electrons are like rambunctious, hyperactive children running around in circles that don't make sense around the atom, right? So incredibly hard to study. So how do electrons, I can't even read this because I have my annotation stuff in the way, get what they want so they can do their job? There we go. They configure, right? Electron configuration is the title of this lesson that we're going to be reviewing. Now, I'm not covering every single detail in the lesson. You probably noticed it's very detailed, right? It probably should have been broken up into 3 lessons, I would say. But I'm going to touch on the main things, specifically the shortcuts. So there's several levels, right? And here we're talking about energy levels, right? We abbreviate them as S, P, D, and F. There's 4. They have different rules. They have different requirements. We'll look at that in a second. Here's another little fun fact about electrons. They can actually form pairs because they have opposite spins. So that allows them to actually be next to each other without being as compromised. So think about it if you're on the bus. Usually you have to sit side by side with someone. Well, imagine if your seat was facing this direction and that person was facing a different way. You might be more likely to sit there, right, than if you have to sit right next to them. So electrons spin in opposite directions in their pair, and that allows them to actually be near each other, and then, of course, be closer to the nucleus, which makes them happy. So let's talk about these levels. They look like these pictures. Now, how do we know this? Orbits, yes. How do we know this? Oof. It's a theory, right? There's a lot of evidence. People have tested this stuff in the lab, tracing these orbitals or the paths that the electrons take, right, as best as they can, and they've come up with this system. So the S energy level or orbital, right? I guess it's not an energy level technically, but it's an orbital, is spherical shaped, right? It's the closest to the nucleus usually, and it can hold 2 electrons, right? The P orbital can hold up to 6 electrons, right? It has this shape. It looks more like a figure 8. The D orbital, right, is much more complex here. Kind of looks like 2 figure 8s next to each other. And the D orbital can hold 10 electrons. And then the F orbital is the most complex, right? It looks like a bunch of balloons, and it can hold up to 14, right? So electrons are going to go into these, I guess I should change this to orbitals because I wrote energy levels and then I went off on a different tangent, guys. That's what happens when you make this PowerPoint in the night. All right. So what do orbitals look like? So we're going to have something with energy levels, orbitals, and then the number of electrons. These are what the orbitals look like. Energy levels are going to determine how far away they are from the nucleus. So hopefully this is sounding familiar to you, right? This should have been stuff you read about in the lesson. Give me a 1 in the chat if you're with me so far. You're like, okay, I remember reading this. I saw the weird picture things. I got it. Electrons are in orbitals. Okay, we got 2 1s. We'll take that as a okay. All right, so let's talk about the shortcut, which some of you guys might have already figured out the shortcut. This is how we actually can label the periodic table into those orbitals, the S, D, P, and F. So I would 100% recommend printing this, saving this picture, making your own version of this, right? Because this is going to help you tremendously when you have to try to write the electron configuration. The only weird thing that is done here that kind of has to be done in order for this to work is helium actually kind of gets moved over here next to hydrogen, right? Because helium is part of the S orbital in terms of the periodic table. D is going to be these middle ones here, P on the right side, and then F down here in our rarely used elements, although we will see some of those. So how do we do this in the shortcut way? Well, we figure out what element we want to find our electron configuration for. So let's say we want to find it for sulfur. I'm going to get my little spotlight here. Sulfur, right? We find sulfur on the periodic table. It's number 16. That tells us that there are 16 electrons. So we should make sure we know that at the end, we need to have 16 electrons. And now we're literally just going to follow each row of the periodic table, writing out our configuration. So we start up here in 1. There can be 2 electrons in the S orbital, right? And we are not looking for hydrogen or helium. We need to keep going. So we know then that our first energy level, because it's the first row, 1s2, is going to be part of our electron configuration. Okay, that's the whole first row, right? Because remember, helium has been taken over to the S side. Our second row, we start at S again. This time we're in our second row, so we're going to be in our second energy level. We're going to have a 2s2, because again, we have 2 electrons, right? And in this case, we're literally counting the squares. That's it. 2 electrons there. Then D is not here, right? D doesn't start until you get down here into the 4th energy level. So we just cut straight across to our P, and we see that we need to go 1, 2, 3, 4, 5, 6, and we still haven't gotten to sulfur. So that's going to tell us that we are still in 2, right? We're still in our 2nd row. We're in the p orbital now, and we can have 6 electrons in there. We also could just count that we have 6 periodic table boxes. Oops, why can't I select this? Sorry, guys, I'm having tech issues. I want to make it look pretty. Okay. And then we keep going. We go to our 3rd energy level, where we're back to S, and we have 2 S again, or 2 electrons in the S. Tech. So we write our 3rd energy level, 3s2, right? Remember, this last letter or last number here is telling you the number of electrons. And then we come back across to P, right? Still no D. We're not in our 4th energy level yet. And we need to go to sulfur. So we see 1, 2, 3, 4. So we're going to have 3p4. And that's going to be our entire electron configuration for sulfur, right? And we can double check it by saying, well, do we have 16 electrons? Let's see, 4, 5, 6, 12, 13, 14, 15, 16. We do. Right, so really it's just about going across the periodic table, and you don't even have to remember how many electrons are in each one, because each box counts as an electron, right? So as you go across, we're going to do more examples of this. You can just count and write out 1s, blah, 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 2s, 2p, et cetera, until you get to where your element is. Now, the tricky thing is when you get down here into the F, right? Because F is technically situated right here, so that the periodic table is actually longer, right? But it won't fit on a paper if we have it huge with you able to see it. So you have to remember that if you get down here and you're still going, right, you have to jump down into your F and go across F before you can go to D. Okay. Why is 53 circled? I don't know, because I stole this from someone else because I thought it was beautiful how they wrote S, D, P, and F humongously. And I'm guessing that they used that one as an example, but I used sulfur instead. So 53 is not circled for any particular reason. It was just probably somebody else's example. Okay, so I know this is really complicated and confusing and it's hard to explain, so we're gonna keep practicing it. But just let me know here, do we have any questions so far, right? And does this seem helpful to you? I hope so. I hope it's helpful. So we're going to try again with, except that I already showed you the answer here, but we're going to try with carbon to make sure that this works. Right, so carbon, we go back to our periodic table. We find our carbon. It's number 6. Right, so we need to get to carbon. So we start at the top. We're going to go for our whole first row here. We're going to have 1s2. Then we're going to come into our second row to get 2s2. And then we're going to come into our p's here and get 2p2, right? Because we only had to fill 2 boxes in the p. And that would be our electron configuration for carbon. We could double check, right? Does this equal 6 electrons? 2, 4, 6. It does, right? So that is our configuration, right? I find this so much easier than having to try to remember all of this in order because, right, this helps you get everything in the right order as well. It gets the S, the Ds, and the Ps in the right order. Because sometimes it can be confusing, especially when D gets involved. When do we add D? When do we add those D orbitals in? they don't come in until the 4th energy level. So they're not even going to be in existence for anything under atomic number 21. We'll have no d orbitals, right? So that's something to keep in mind, right? That if you're using the periodic table to help you do this, it's going to keep the orbitals in the correct order for you, because the order doesn't necessarily come intuitively here. So that was carbon, okay? Let's try for oxygen. Did I pick a harder one? I didn't. Let's do 2. We're going to do them independently, and then we're going to compare. So let's do oxygen, and let's do krypton. Okay, so try this method. You could also use your own method if you have your own way of doing it, that's fine. See if you can write out the electron configuration for both oxygen and krypton. All right, I'm gonna wait for you guys to post possibilities in the chat. I agree with you, Janie Mae. I got the same thing for oxygen. 1s2, 2s2, 2p4, right? And we could double check the number of electrons, 4, 5, 6, 7, 8. We got 8 electrons, it looks good. Now krypton is gonna be a little bit more intense, right? Because it is number 36. So let's see if we can get some answers for that one. And I appreciate, Janie Mae, that you put the exponent little caret in there, right? Because it is the electrons should be as an exponent, which is not super easy to do on the computer. So if you write it with a space in between, that is fine. But if you're writing it by hand, you want to use that exponent. Okay, we got 2 krypton answers, 3 krypton answers, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4d10, 4p6. That's exactly what I got. All right, if you did not get that yet, right, you might just need to keep practicing. I'm telling you, this is very weird at first, right? Especially because this shortcut kind of takes away the background of why this is important. But just remember that these rows in the periodic table are actually our energy levels, right? So the energy is increasing as we go down. And the S, D, P, and F are representing those orbitals or where those electrons are actually positioned, right? And it's so amazing that it happens to conveniently fit on the periodic table in such a beautiful way, because it could be much worse. It's actually amazing how the periodic table works, guys. Like, there's so much that you can do just from looking at it, which is insane that some guy, before he even knew any of this, made this periodic table. Like, I just can't believe that. Very impressive stuff. All right. So we did oxygen. Okay. Now the other thing is, here's another shortcut that they did kind of talk about in the lesson. You can actually use this noble gas notation, right, which is a shortcut. Because, for example, krypton is a noble gas, so we couldn't really write just krypton as its electron configuration. But if they're asking for something that is after a noble gas, for example, gold, which we'll look at in a second, right, then you can actually say the previous noble gas in brackets and then write from there what you got. So if we look at gold, which is right here, I was like having a hard time. I was like, is it AG or AU? AU, here's gold, right? We can actually say that we can take this xenon gas and then just do our notation for only this row that gold is in. Which actually, I think I see a mistake with my notation. I don't think it includes this S level here. 1, 2, 3, 4, 5, 6. Oh, it does. It's just written at the end. So we should get 6S2, 6D, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that should be it, right? Oh, nope, I forgot F. We got to have F in there, right? Because we have this little star here, which tells us we have to come down to this row, which I completely forgot about. See why I'm telling you the F1 will get you confused, because the periodic table is actually much longer than we are visibly seeing here. So, oops. Oh, I wanted to try for a whole bunch of other things. And I had the chat blocking it. That's okay. We don't need to do more. I think we're good on this so far. So then here we have all of this written out. They did not write it in the order that the periodic table did it, because I actually just copied this from the internet. Because guess what? If you need to check any of these, you can Google it, right? All of the elements have their electron configuration out there. So you can always check it, but it's important to know how to do it, right? Because I will ask you on the DBA today how you do this electron configuration. So you need to be able to explain it in your own words how you do it. And the answer is not Google it, even though you could to check it, right? But regardless, once you get up into these higher numbers, you can use the noble gas right before and then only do the row that that element is in. Okay, so then the lesson takes a turn and goes into actual orbital notation, specifically the electrons and their orientation, right? So this shows electrons in pairs, and the arrows represent those opposite spins that I was talking about earlier. So when you see an electron pair, you see it written with an arrow facing opposite directions, right? Because that is telling you that one electron is spinning one way and the other one is spinning the opposite way. Really, this is going to be where that bus thing comes back into account. In an orbital, electrons are going to fill one slot in the pair before they'll start pairing up, right? Same thing like with seats on the bus. You're going to take an open pair of seats before you're going to pair up with a stranger. And electrons are the same way, right? So these two electrons here would much rather be separated than be a pair. They don't have to be a pair, so they won't. So let's try it with Fe. We're going to write the electron configuration, And we're also going to draw the spins, which sounds kind of funny. Draw the spins. So I'll go back to my periodic table. You might have your own open. Find Fe, or iron, right? Hint, it's in the D section. And you're going to write the electron configuration, and then also draw the spins and what those electrons will look like in. I'm going to get paper to draw on. Let me see if I can annotate this where it doesn't look awful. No guarantees. Is it okay with you guys if I click away from the periodic table? Yes, no? Okay, I'm gonna click away. You can always Google a periodic table if you need to look at one. Okay. My electrons are not very orderly. Oops, that's supposed to be 3p. Okay, so you should have got something like this, right? Except hopefully your arrows look prettier. Now, you may be thinking, do I have to draw the boxes, right, like they drew? You don't have to, right? But you want to be keeping in your mind that mentality that electrons are going to pair up, right? And you're also going to need to know how many possible electrons there could be. For example, in your s orbitals, you're only ever going to have 2. So if you have 2 electrons, they're going to pair up, right? The only situation where you're going to have an s orbital where there isn't something in it is if you're in the far left column of the periodic table, right? You're a hydrogen, lithium, sodium, potassium, etc. Because then you're only going to have 1 electron in that s orbital. Otherwise, you're going to have 2, right? P, you can have up to 6 electrons or 3 pairs. You're not sure? Look at the periodic table, right? It's going to get very sloppy here for a second, but you can count how many boxes there are for P. 1, 2, 3, 4, 5, 6. That means there's 6 possible electrons there. If they pair up, right, then that means that there are 3 pairs of electrons. For D, you could count the squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means there could be 5 possible pairings for D, right? And then F is going to be 14 electrons or 7 possible pairs. So you don't have to memorize that necessarily. You can use the periodic table to tell you that, right? But the most important step here is when you get to the end, right? These last 6 electrons in the d orbital, if you drew your electrons like this, you are wrong, right? Because they would not pair up when there are 5 seats, shall we say, on the bus, or 5 seats to fill, right? So in this case, they're going to fill 1, 2, 3, 4, 5, and then the last 6th electron here will begrudgingly pair up and fill in that first seat, right? So keep that in mind. They're not going to make pairs unless they have to. So that might take some practicing, right, to sort of line out those arrows representing the spins, right, and really just thinking about, okay, each one is going to take 1 part of the pair before they start pairing up. Does that make sense to you guys? Can you give me a 1 in the chat if you're like, I get it, or a 2 if you're like, I have no idea? Okay, good. I'm glad you guys are following me. This is a lot, I know. So I'm just trying to give you some shortcuts though, so that it's, oh, I have to erase each one of these arrows individually. Are you kidding me? Oh wait, can I do it like this? Zoom is so weird. I'm like dragging the eraser and it doesn't erase. Now, it's like a special program for getting credits. Okay. Sorry, I was having a side conversation, guys, while I was erasing these freaking arrows. Okay, they're gone. Whew. So then there are 2 rules, right, that we actually just went through shortcuts on how to do, but I wanted to ask you guys, what are these rules? How could we summarize these rules in a way that makes sense to us, right? Because then we could always just say, oh, well, we're following Hund's rule or the Aufbau principle, but it's kind of a rule too. So what would we say are the definitions of these rules? I'll wait for you guys. Feel free to Google, feel free to look in your notes, right? What do these rules or principles mean and what could we summarize them as? All right, Abby tells us Hund's rule, those with the same charge repel each other and spread out in the orbital. Excellent. So this is talking about the spins, right? So those, or we'll say electrons with the same charge repel each other and spread out in the orbital, aka electrons do not want to sit next to each other on the bus. Right, they're going to spread out until they have to pair up. So that would be when we see our arrows doing something like this, in, we could say, our p orbital, right? If we have 4 electrons, they're going to look like this, rather than being 2 sets of pairs. And then what about Aufbau? What is the Aufbau principle? My internet connection is unstable. What is it? All right. Aufbau. I just like saying Aufbau. Someone maybe other than Abby could suggest what Aufbau is telling us here. Great. Electrons occupy the lowest energy orbital possible, right? So this is going to be that shortcut on the periodic table, right, will help you always do this. Because that's going to tell you that you're starting in 1s, going to 2s, going to 2p, going to 3s, etc. Right? It's going to keep you keeping those electrons in the lowest energy orbital possible. Okay, so just making sure that we kind of understand the science principles behind these concepts here, right? And not just the shortcuts, although let's not lie, I haven't taken a chemistry class in over 10 years and I mostly remember the shortcuts, not these guys. Right? So it's important to know where it's coming from, but if you can actually do the electron configuration and you can follow these rules without necessarily knowing what they are, that's fine. Right? But just keep in mind, that's where they came from, was these 2 scientists here. All right. So last quick thing here, which is probably going to be a review for most of us. But again, there's a valence electron shortcut, right? The way that they explained this in the Canvas lesson, I thought personally was confusing, right? And I know what valence electrons are already. So valence electrons are the outermost electrons. They're the electrons that are involved in bonding, right? So that's going to be super important for the next stuff that we're going to talk about. We're going to talk about chemical bonds. So we're kind of ignoring the metals here, mostly because metals have, mostly their valence electron number is 2, but sometimes it's 3, sometimes it's 1, it depends. So we're going to leave them blank for now. But we do know that every single element in group 1 has 1 valence electron. Every element in group 2 has 2 valence electrons. 3, 4, 5, 6, 7, 8, and then helium, of course, is special, right? Because really it kind of belongs over here next to hydrogen. But we have it in this column because it's a noble gas, right? Because its s orbital is completely full, it acts exactly like these noble gases do. Because their p orbitals are full. So they're going to have similar properties. So I would definitely know this, right? Because that's going to give you a quick little reference. How many valence electrons does that element have, just from looking at the periodic table? All of the elements in the same group are going to react very similarly, right? If they have the same valence electron number, their reactions are going to be very similar, and their bonding is going to be very similar. For example, everybody in group 7 really likes everybody in group 1 because they want to get to 8 valence electrons so they can have a full shell, right? So group 7 loves to bond with group 1, and it doesn't matter which energy level they're in or which row, right? they want to bond because they want to fill that shell. So we'll talk more about that when we get into bonding. But then the lesson also talks about Lewis dot structure, which I think should be a separate lesson, but I will quickly describe it to you guys here, and then I'm going to have to get ready to do my earth science lab. But Lewis dot structures, all they do is show only the valence electrons. They don't show any other electrons. The element could have 70 electrons. The Lewis dot structure, the most it could show is 8, right? Because 8 is the highest number of valence electrons you can have. So it also shows the correct distribution, the concept that electrons will form singles first before they form pairs. So what does this look like, right? I thought I drew, do I have, oh, my chat's blocking it again. I'm like, I thought I drew one. Chlorine, right? If we go to the periodic table and we look for chlorine, we see that it's in group 7, which means that it has 7 valence electrons. This is how we would draw a Lewis dot structure. We draw the element's symbol, and then we literally plop down the dots around it to show us how many electrons it has. And guess what? This shows us in a nice visual way that it really only needs 1 electron to be complete, right? So that's awesome, because then if we know something in group 1, we could say, oh yeah, it's probably going to bond with chlorine. So let's try to draw a few. We won't do all of these because we'll do helium because it's an exception. And let's do boron. Let's do boron and helium. You guys can try calcium and hydrogen on your own. But look at boron on the periodic table. You might have to pull one up for a quick second. And I'll give you a hint that it's in group 3. Or valence electron group 3. So we're going to want to draw the symbol for boron, which is a B. And then we're actually going to take little dots, and we have 3 valence electrons. So where are they going to go? I drew one there. What do you guys think? Where are the other ones going to go? I know you can't really draw in the chat, but should I do it like this? Or counterclockwise? Yeah. There's a technical way to do it. You're right. So I should start at the top then, right? And counterclockwise means I'm going to go to the left, you're telling me, and then to the bottom. Are we feeling better about that? Okay. Right, if you drew it this way, the first way I drew it, not the technical notation, right, but still showing the same thing. So I would not count points off for that. I'd be like, cool, you knew there were 3 valence electrons and you drew them, right, unpaired. Okay, now what about helium? Helium is special because it is a noble gas. Oh no, why can't I erase this? There we go. For helium, this is the only element where we actually are going to see a pair straight up. I can't draw my circles evenly, but they're supposed to be the same, right? Because helium has its valence shell full. It only has 2 electrons possible in its valence shell, and they're full. So in other words, those electrons are forced to pair up, right? Helium is the only time that you're going to see that. Otherwise, you should, as you guys stated, do counterclockwise, put 1 electron on each side, and then go back and add pairs if there's more than 4 valence electrons. Right, the drawing of these is not super hard, but it can be confusing, right, if you don't know the valence electron number, which is why I showed you that little shortcut cheat on how to figure that out. So we're going to come back to this when we talk about bonding, because I'm pretty sure I show on the next slide. Why do we care about this, right? Well, the Lewis structures help us with bonding and identifying which elements can bond with each other. So for example, we have a sodium and a chlorine here, right? They drew the Lewis dot structures. They did not go counterclockwise unless they're starting there, but regardless, I guess they did if they started there. We see that sodium has 1 valence electron and chlorine has 7. And guess what? These two bond super easily and they form salt, right? This electron actually gets donated to the chlorine. The sodium takes on a positive charge and the chlorine takes on a negative charge. And then they actually stick to each other. So when we talk about bonding, we're going to find out, right, that sodium will actually donate its electron to chlorine so that it has 0 valence electrons, and it's actually satisfied that way, right? Because sodium would have to get 7 electrons to satisfy its shell, and it knows that's not possible. It just gives its electron up. It's like, okay, well, it's gone. Everything is even and balanced now. Right, so you can kind of think about elements as being slightly OCD. They want to have 8 valence electrons, right, and they're willing to negotiate in order to get there. So that's going to be important when we come into talking about bonding, right, is being able to draw these Lewis structures and sort of show the electrons and how many there are in the valence electrons. Okay, we're going to do the DBA super, super quick here because this took a lot longer for me to explain than I thought. We're going to go into this Google Doc, which I will send a link to you guys in the chat. If you already did your DBA, Janie Mae, I know we did ours yesterday. You're welcome to leave, right? We're just going to do the DBA, and that's the end of it. There is a code word, which, give me 1 second. Let me look at what it is, because I forgot already. The code word for today is, and you can use that code word to get 2 bonus points on your electron configuration quiz, or if you get 100 on that quiz, on any quiz of your choice, just let me know, right? So knowing the code word will help you get some bonus points on your quiz. Everybody else who is going to do the DBA now, please make your way into the Google Doc. By the way, I also included here a Khan Academy video that will actually help you kind of go through this electron configuration process. If you want to watch more examples, right, you need some more practice, that is a good video to watch. And they probably explain it even better than I do. So in our Google Doc here, go ahead and put your name in one of the boxes if you would like to participate in this DBA. Bye, Janie Mae. Thank you for being an excellent participant today. And we're going to just do 3 questions really quickly. You're going to type your answer to the question next to your name. Okay, so I'm going to go ahead and start just because we really don't have too much time left. First question is going to be, I'm trying to remember what we even learned about in this module. Oops, that's a weather. I was thinking I could get a little reminder. Well, we'll just start with the hardest question first. How do you configure an electron? How do you write out electron configuration? Just give me a general description of how you do that. And you're just going to type your answer in the box. You could say you use the periodic table, you look for the orbitals, right? Whatever description you want to say. Go through the rows on the periodic table, good. Try to add something in there about orbitals, right? Or SDFP, something like that, that you look for the orbital level, the energy level, something like that. Okay, the last two questions, I actually wrote, this is not for earth science yet. Sorry, Devin, we haven't started. We still got 4 minutes left here. And Kim, you're welcome to hang out though until we start. I wrote the other two questions here in the document, right? Because I'm actually going to end this class in about 1 minute. So I have time to use the bathroom really quickly before I start earth science. And you guys are welcome to take as much time as you'd like to write something here. I'm going to come back to this and put grades in for DBAs based on this, right? Make sure you're using your own words and you're not copying what someone else said. So our second question is going to be, how can we find the number of neutrons in an atom? And then what was one thing you took away from this module? So like something that you learned, something that you thought was important. Okay. And I will leave you guys comments if there's something that you wrote that I think needs clarification, or maybe I'm not quite sure what you meant. Otherwise, I'm going to end this meeting here, and I do have another announcement, which I'll also send you a note about. Next Friday, we don't have a virtual session. I'm going to be out of town. I'm going to be at a wedding, so I'm not going to be able to do a virtual session next Friday. Okay, so you'll also get an email telling you about that. All right, otherwise, you guys keep filling in for those questions for the DBA, and I will see you guys in 2 weeks.